Let me hide that. All right, so we are going to discuss the fundamental theorem of algebra. Let me see if I can put this where I can. I think my battery's good. No, my battery is not good. Let me plug this in before I run out of battery. All right. So, fundamental theorem of algebra. This is the fifth section out of chapter 2. I think there's a total of 8 sections. So, we're starting to get towards the end of this chapter. Here's what we're specifically been doing. Use the fundamental theorem of algebra to determine the number of zeros of a polynomial function. And then we're spending most of the time really finding the zeros of polynomial functions. So this is the big one that we're going to be doing most of the time today, finding all zeros of a polynomial function, including complex zeros. Find conjugate pairs of complex zeros, and find zeros of polynomials by factoring. So we are going to do some factoring also. Clear all drawings. I don't know why that's not clearing. Maybe it's just staying with that. I don't know. All right, so fundamental theorem of algebra. There we go. We know that an nth degree polynomial can have at most n real zeros. So what we're saying is if we have a polynomial that is 4th degree, we talked about this in the past, it can at most have 4 real zeros, real number zeros, right? Which means there's no I in it, at most. Well, in the complex number system, this statement can be improvised. That is, in the complex number system, every nth degree polynomial function has precisely n zeros. So once we pull in complex numbers and imaginary numbers with the I, what we can say is the degree of the polynomial tells us exactly how many zeros there are, because it will include both real zeros and complex zeros. So that's basically what the fundamental theorem of algebra says. It says if it's a 4th degree polynomial, there's going to be 4 zeros, either complex or real. They could all be real, but they don't have to be. There can be some complex ones in there. All right. Which, if you're interested in history, the first proven by the German mathematician Carl Friedrich Gauss, who died in 1855. Says if f of x is a polynomial of degree n, where n is greater than 0, then f has at least 1 0 in the complex number system. So complex number system includes both the reals and the imaginaries, right? Remember that. All right. That doesn't really help us. All right. Note that neither the fundamental theorem of algebra nor the linear factorization theorem tells you how to find the zeros or factor of a polynomial. Such theorems are called existence theorems. To find the zeros of a polynomial function, you still must rely on other techniques. Basically, to find these zeros, we're going to use some of the things we've done previously. Is we're going to use factoring. We're going to use long division. We might use the calculator to help us to find where it's crossing. Just remember, when we're talking about the graph of a polynomial, all right, we've got a couple things that if a graph crosses the x-axis in just sort of a normal crossing position, that indicates one real zero. If it's like the bottom of a parabola where it touches the x-axis and then immediately bounces back and starts going the other direction, that represents two zeros at that one point, right? We talked about repeated repeated zeros. And then if it's like x cubed where it goes through the x-axis and it has that little flatten out and then back in like one of these little things where we hear it goes down here and then it flattens out and then does this, one of these little things here. That could represent three zeros, three real zeros. But what we're going to look at today is more of the factoring and things like that. All right, so let's just refresh our memory here on this real quick. The first degree polynomial, such if we have f of x equals x minus 2, that's a degree 1 polynomial. It has 1, 0, right? If we looked at the graph of that, that's simply a graph that goes through the y-axis at -2 and has a slope of up 1 over 1, would look something like that right there, right? It crosses the x-axis in one spot. All right. Counting multiplicity, the second degree polynomial x squared minus 6x plus 9, which when factored is x minus 3 times x minus 3. All right, what this is this is a parabola who has a 0 at x equals 3, and what is happening is this parabola is basically sitting right on the x-axis right there. That represents two zeros when it bounces up like that. All right. Third degree polynomial function. Notice this one. There are three zeros here, two of which are complex. Okay. And what you're going to notice is complex zeros, imaginary zeros come in pairs. Okay. And if you notice, you have x minus 2i and x plus 2i are the factors. Now notice right here, make sure we understand this. I don't think we have any problem, right? Once we have it in factored form, what we do is we set each factor equal to 0. So in this case, we know x equals 0. So 0 is one of our zeros. The other one, x minus 2i equals 0. So what we would do is we would add 2i to both sides, and I would get x equals 2i. And then the same thing, x plus 2i equals 0. I would subtract 2i and I get negative 2i. That's how they get these three zeros. The zeros equal 0, 2i, and negative 2i. Because once it was factored. Now, I want you to notice this too, how they factored this. This is going to be something we're using today right here. They're basing it off a difference of squares. Okay? If you remember, factoring a difference of squares, if we have a perfect square minus a perfect square, to factor that, you take the square root of the first term, you take the square root of the second term, and then one of them's plus, one of them's minus. Okay? Well, if we have a plus, like that, x plus 4. Now, normally, if we're just dealing with real numbers, that will not factor. But now, because we're talking about complex and imaginary numbers, we can take the square root of a negative number, which is I, right? So what we had there, well, notice what happens is whenever this is a plus, what it does is we can take x and x still, and then we can take the square root of negative 4, which would be 2i, and 2i, and then one of them's a plus and one of them's a minus. Okay? So now that we have imaginary numbers, that will factor. Notice what happens when I multiply that back out. X times x is x squared. We're still going to have the middle two terms add to 0. X times negative 2i is negative 2ix. 2i times x is positive 2ix, and then 2i times a negative 2i is negative 4i squared, right? Well, these two add to 0, and notice what we have. We said I squared always equals negative 1, right? So negative 4 times negative 1 is positive 4. Okay? So we're sort of bringing in the fact now that we can use a difference of squares type factoring when it is a plus. It just turns it into imaginary numbers. Okay? So be aware of that when we go a little bit further. And notice it's the same thing happening right here in the fourth degree. Fourth degree means there's going to be 4 zeros, which means it has 4 factors. And notice what they did is it sets up as x4 minus 1 is going to be x squared minus 1, x squared plus 1. Now, x squared minus 1 is just a normal difference of squares. So that's going to be x plus 1, x minus 1. But this one, because it's a plus, becomes x plus I, x minus I. And that's where they get the total 4 factors from. And then that's where they get the 4 zeros of 1, negative 1, I, and negative I. Because when you set all those equal to 0 and solve, that becomes negative 1. This becomes positive 1. This becomes negative I. This becomes positive I. All right. So that's going to start coming into play as we do this. So this is what we're going to be. This is the main part of what we're doing today. Are finding zeros of polynomial functions. Okay. And all right. Remember that the n zeros of a polynomial function can be real or complex. They may be repeated. Example 2 here illustrates several cases. All right. Let's see what example 2 is. All right. So I'm going to. They're talking about x cubed plus 4x. So f of x equals x cubed. I didn't write that. All right, so f of x equals x cubed plus 4x. All right, and they're wanting us to completely factor that so that we can find all the zeros. Right, once we completely factor something, we can set each factor equal to 0. And actually, I'll show you a couple ways to do this. You could actually get to this answer. All right, so what they're doing here when they factor it, first of all, right, we always have to factor out the common factor. Well, right here, there's an x common to both terms. So when I factor out the x, I'll be left with x squared plus 4. Now that becomes, just like we just talked about, now that we've got imaginary numbers, we can factor x squared plus 4. So we're going to have x, and then that's going to be x plus 2i, x minus 2i. And so that's how they got these 3 factors. So if I want to find the 3 zeros, I just now set each one of these equal to 0. So x equals 0 is one of them. X plus 2i equals 0. I subtract 2i and I get x equals negative 2i. That's a 0. And then x minus 2i equals 0. I add 2i and I get x equals 2i. That is 3 zeros. All right. Another way that you could have gotten to this result without completely factoring is if I had started right here and just set both of those equal to 0, x equals 0, and then that's one of them, and then x squared plus 4 equals 0. What I could have done is subtract 4, and I would have had x squared equals negative 4, and then I would have taken the square root of both sides. And remember, when you take the square root inside of an equation, you've got to include both the positive and the negative result. And then the square root of negative 4 is 2i, right? And there's my other 2 zeros. So either way, I'm getting the same two or the same three zeros, whether I'm factoring it all the way out or once I got x squared plus a number, okay, because of that square root theorem, whatever, to allow you to solve equations. I could go ahead and set that equal to 0 because there's not an x term there, and take the square root of that negative number. All right. So those are the three zeros. Now, when I'm looking at the graph of this, imaginary zeros do not indicate, we cannot see those on the graph at all. The graph shows us nothing about where complex zeros are because it's not in a place where it crosses the x-axis. So this graph is only going to cross the x-axis at 0. And I think this is what the graph looks like right here. All right, if you'll notice, there's the graph of that. Okay, it only crosses the x-axis in one spot. So that's why we've got to be able to find the all complex zeros and real zeros. We've got to be able to do some algebra with it because you can't look at a graph. Okay. But the real zeros do show up. Imaginary zeros do not. Okay. So, conjugate pairs. All right. So pay attention to this. This is important. All right. Two complex zeros are conjugates. That is, they are of the forms a plus bi and a minus bi. So we talked about conjugates the other day, right? If we had 3 minus 4i, the conjugate of that was simply 3 plus 4i. If I have negative 2 minus 6i, the complex conjugate, we just changed the sign in the middle, is negative 2 plus 6i, right? Conjugates. Because what happens when I multiply conjugates back out, they turn into real, right? They don't necessarily turn into real, but they do. They turn into a single number because the middle two terms add to 0. The last term turns to I squared, which we changes it to a negative. All right. So let f of x be a polynomial function that has real coefficients. All right. So we're talking about a polynomial that doesn't have i's anywhere within the polynomial. That's what we're doing on all of these. All right. There's no imaginary parts to the polynomial. If a plus bi, where b is not equal to 0, is 0 of the function, then the conjugate is also a 0 of the function. So what that is saying is if we have a polynomial and it has an imaginary 0, it's going to have at least 2 imaginary zeros because whatever 0 is there that's complex, its conjugate is also a 0 of that polynomial. So if you know one complex or imaginary 0 of a polynomial, you know 2 because you now know that they are conjugates. So if you know one of them, you know the other one by the fact that it is a conjugate. Okay? Be sure you see that this result is true only when the polynomial function has real coefficients. For instance, the result applies to the function x squared plus 1, but not the function x minus I. So if we've got a polynomial that's got imaginary terms within the polynomial, this does not hold true. It is only when we have a polynomial like this right here, okay, that has only real parts of the polynomial. And then notice if we solve that, set that x squared plus 1 equal to 0 and solve it, we would get x squared equals negative 1. We take the square root of both sides, which means x equals plus or minus I. Well, we have positive I and we have negative I. If I were to write those in complete complex number form, that would be 0 plus I, 0 minus I. Let me write that bigger. 0 plus I and 0 minus I. Notice those are conjugates. All right. So we know if I is a 0, negative I has to be a 0. All right. Like up here, if 3 minus 4i is a 0 of a polynomial, then this conjugate is also a 0 of that polynomial. Okay. So be sure we are aware of that as we're going through here. All right. So watch how this one works. This one is wanting us to find a polynomial that has real zeros, or has zeros of -1, and 3i. All right. Now it says a fourth degree polynomial, and they're only giving us 3 zeros. What is the missing zero there that we know has to be there? -1, -1. Here is an imaginary zero, which means if it has an imaginary zero, its conjugate also has to be a zero, which means -3i is also a zero of this. So if they want us to write the polynomial function, all right, I'm going to shrink that down. Here are our zeros. X equals -1, -1, 3i, and -3i. So what I would do is I would write out the factors that each one of these zeros came from. X minus 1 comes from the factor of x plus 1. Would everybody agree with that? -1, that's a repeated factor of x plus 1. Well, what factor does 3i come from? Well, it comes from x minus 3i. And -3i comes from x plus 3i. Okay? So those are all my factors of the function. So to find my polynomial, all I have to do is multiply all that out. Okay? I have to FOIL it all back out. So what I'm going to do is I'm going to multiply these two together first. X times x, so f of x is going to equal x squared plus x plus 1. And then I'm going to multiply out these two conjugates. I'm going to drop down below it because I'm running out of space there. But x times x is x squared plus 3ix. So x times 3i is 3ix, right? And then minus 3ix. And then -3i times positive 3i would be -9i squared. All right. Now, I'm about to run out of room, but this is going to be what? X squared plus 2x plus 1. And this one is going to be x squared 3ix minus 3ix. And -9i squared is equal to positive 9, right? So that is x squared plus 9. All right, now I've got a trinomial times a binomial, so I've got to go ahead and multiply these together. So I've got to distribute the x squared. So x squared times x squared is x to the fourth, which I know I've got to find an x to the fourth somewhere because this is a fourth degree polynomial. 4 zeros, so I know that this is going to be a degree 4 polynomial, so it makes sense that I've got an x to the fourth there. X squared times 9 would be a positive 9x squared. And then 2x times x squared would be a positive 2x cubed. 2x times 9 would be 18x. Then 1 times x squared would be x squared. And then 1 times 9 is 9. Now I just need to simply combine all my like terms. And I have x to the fourth plus 2x cubed. 9x squared plus x squared would be 10x squared. That's the only x term, plus 18x plus 9. And there is the polynomial that has those 4 zeros. Okay? So if you have the zeros given to you and it wants you to find a polynomial, you simply take those zeros and put them in the factors they would have come from. Right? -1 comes from the factor of x plus 1. 3i comes from the factor of x minus 3i. and so on. Then what you do is you just multiply those all together, back together. The i's are going to disappear, right? Because they say it comes from it becomes from real number coefficients. And then you just got to do the distribution, distributing correctly and simplifying, combining like terms correctly. Okay? So that's one thing that's a major thing we want to be able to do is given zeros, and they don't have to give you all the complex zeros. All they have to do is give you one of them because the conjugate's going to be there. Right? If we see one complex or imaginary zero, we know the conjugate is there also. Okay? So that's what we did there. All right? So it's just a matter of, it's really nothing new. It's just sort of looking at it a little bit different. And then the process of everything you've done before. All right. Now, talk about factoring. All right. So now we're going to talk about going the other direction. Okay. We're going to be starting with a polynomial and we're going to look at factoring. Sometimes they're going to give you one of the zeros first because it won't factor until we can divide out at least one of the zeros or possibly two of them. So the linear factorization theorem states that you can write any nth degree polynomial as a product of n linear factors. So all that's saying is if we've got a fifth degree polynomial, we can write it as 5 factors multiplied together, right? This result, however, concludes the possibility that some of the values of CI are complex, right? Because of the fundamental theorem of algebra states that if you have a polynomial fifth degree, there's exactly 5 zeros, but they don't all have to be real. They can be imaginary too. All right. The following theorem states that even when you do not want to get involved with complex factors, you can still write f of x as the product of linear and quadratic factors. Every polynomial of degree n greater than 0 with real coefficients can be written as the product of linear quadratic factors with real coefficients, where the quadratic factors have no real zeros. All right, a quadratic factor with no real zeros is said to be prime or irreducible over reals. Be sure you see that this is not the same as being irreducible over rationals. For example, the quadratic. All right, so the factor of x squared plus 1. Okay, we've talked about how now if we're looking at complex numbers, we could write that as x minus 1, not x minus 1, x minus I, x plus I. If it was x squared minus 1, it would go x minus 1, x plus 1. But x squared plus 1 factors as imaginary. So x squared plus 1 is irreducible over the reals. All right? So when they say it is irreducible over the reals, it means that we cannot factor that without using imaginary parts. So I would have to, if I was only reducing it over the reals, I would have to leave it as x squared plus 1. All right? I believe that's what that's trying to say. Now, on the other hand, the quadratic x squared minus 2 is irreducible over the rationals, but reducible over the reals. So here's what this is saying. Notice we would normally not be able to factor x squared minus 2, right? Whenever you've done factoring in integrated 3 or whatever, you're always just dealing with real numbers. We're not dealing, I'm talking about you're just dealing with rational numbers, okay? But when you look at all the real numbers, it is factorable over irrational numbers because the square root, we know that for that second term, you take the square root of the second term of each factor, you take the square root of the second term of the original. So normally we only do this difference of squares if it's x squared minus 9. right? We can do that because x and x, square root of 9 is 3 and 3, and we get 1's plus, 1's a minus. We don't normally factor it into square roots.
You get a new computer.
I get a new computer?
You do. You want
Wow.
to install today?
Sure. I'm not using this one, so
I'll do it now. Yeah, you can.
I mean, if y'all would like to, go right ahead.
Of course, it's me that has to. It's all him.
All right.
It's turned off and everything.
No, I can turn it off here. It is now turned off. Okay. So notice right up here, 2 is not normally what we would factor with, but if we're going to reduce it over real numbers, we can take the square root of 2 and put it in both the second positions there. Does that make sense? So x squared minus 2 can actually factor to x minus square root of 2, x plus the square root of 2. Okay? And all this helps whenever we're trying to find zeros, although we could take x squared minus 2 and put it equal to 0. So, all right, so write the polynomial x fourth minus x squared minus 20 as a product of factors that are irreducible over the rational. So if we were just factoring x to the fourth minus x squared minus 20, if I wanted to factor that like you had been taught in integrated 3, okay, we can factor it like a trinomial because that as long as the degree of the first term, the second term, if that degree is half of that, then we can treat it like a normal trinomial, except we just have to go x squared and x squared, correct? And then I need to know what will multiply to negative 20 and add to negative 1 for that middle term, correct? So that would be minus 5 plus 4. So that's all I can do. If I'm going to factor this over rational numbers, that's as far as I can go. Okay, nothing else is reducible. All right. Part B, so this is the A part. I believe that's correct. Let me double check. Yes. All right. Now, if I want to go a step further, B, and I want to factor this over reals, that means I can now take the square root or use the square root of a number. I can't use any i's yet because I'm only talking about real numbers, correct? So if I want to reduce this over reals, the x minus, the one that's a minus, I could go ahead and factor that further. I could factor that as x plus the square root of 5, x minus the square root of 5. I can't do anything with this one because this one, if I factor it any further, it brings in imaginary numbers. So the A part is factored over rational numbers like you've always factored and where you would have to stop. Okay? The second part, it is factored over irrationals, which means I can have square roots. Then the C part, completely factored, means now I can bring in my complex factors. So this would be x plus square root of 5, x minus square root of 5, and then I can go ahead and say this is x plus 2i, x minus 2i. So this is now what we are considered completely factored once we introduce or bring in imaginaries and looking at irrational numbers. Okay? So be aware of that. All right, any questions? All right, and that should be just exactly what we just did. All right, that doesn't really help us. Okay, so here's the last thing we're going to do. We're going to find all the zeros of this right here. And I'm going to try to get through it. All right, we want to find all the zeros of x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. So when we get finished and we're talking about complex and real, this is a fourth degree polynomial, so we've got to have 4 zeros by the time we get finished, correct? They give us 1. We're given that 1 plus 3i is a 0 of f. Well, what do we know about imaginary zeros? If you have 1, you have 2 because the conjugate is also. So what does that mean is also a 0? You would have to agree then that 1 minus 3i is also a 0. So we know 2 of our 4 zeros based on that one statement. Okay? Now, what I need to do is I want to divide out those 2 zeros so that I have a smaller polynomial that I can see if I can factor. So, all right, remember what we said. We said if we have a 0 of x equals I, that comes from the factor of x minus I, correct? So if I have a 0 of 1 plus 3i, that comes from x minus 1 plus 3i. The 0 of 1 plus 3i comes from the factor of x minus that complex number, right? Just like x equals I comes from x minus 1. The 0 of 1 minus 3i comes from x minus that number, 1 minus 3i. Okay, so that's a little bit of a confusing part there because of all the terms. But it's the exact same thing. If I said I had a 0 of x equals negative 5, I think we all understand that comes from the factor of x plus 5. Well, this is a positive. This is the complex number. This is a positive 1 plus 3i, right? Complex numbers just have 2 parts. And this is a positive 1 minus 3i. So it comes from x minus 1 plus 3i, x minus 1 minus 3i. Now, what I'm going to do is I'm going to multiply that together, all right? And then I'm going to divide my result out of that polynomial to see what my 2 zeros I have left are. So, this would be x times x, which is x squared. Then I would have x times negative that. So that's going to be negative x times 1 minus 3i. And then this one's going to be negative 1 plus 3i times x. So this would be negative 1 plus 3i. And then the last one is going to be positive 1 plus 3i times 1 minus 3i. I'm running out of room. 1 plus 3i, 1 minus 3i. All right. So I have x squared. And then what I'm going to do is I'm going to distribute this. So that's negative x plus 3ix. This is negative x minus 3ix. And then when I multiply conjugates, that's going to be 1 times 1, which is 1, plus 3i, minus 3i, minus 9i squared. Now, combine like terms. Notice 3ix minus 3ix, and then 3i minus 3i, that goes away, and I'm left with x squared. Is that the only x? X minus x is minus 2x. And then 1 minus 9i squared, negative 9i squared becomes positive 9, right? because the I squared goes to -1. So that's 1 plus 9, which is 10. So these two factors here multiplied together give me this right here, x squared minus 2x plus 10. Sure thing. All right, now, this factor right here is what leads to my two imaginary results. Now what I have to do is I have to take this and divide this out to see what's left over for my other two. So let's see if I can make some room up here and still see what I'm doing. So what I'm going to do is I'm going to take x to the fourth minus 3x to the third plus 6x squared plus 2x minus 60. And I'm going to do long division. Now, I don't know that we did 3 terms the other day, so pay attention to this. All right, but the process works the same. All right, this first term, x squared times what would give me x to the fourth? That would be x squared. Then I take and distribute through. That's going to be x to the fourth. X squared times negative 2x is negative 2x cubed. And then x squared times 10 would be positive 10x squared. I change the signs, add them together. I've got negative x cubed minus 4x squared, and then I drop down the next one plus 2x. Now, x squared times what is negative x cubed? Negative x. So it would be negative x cubed plus 2x squared plus or minus 10x. I hope I've done this right. I've done it in a little bit of a hurry here. Change the signs, plus, minus, plus. All right, thanks, man. So this is going to be minus 6x squared plus 12x, and then I drop down to minus 60. And then x squared times what would give me negative 6x squared, and that would be a minus 6. Now we know we're going to get a remainder. If we don't get a remainder of 0 here, we've done something wrong, because these are the factors. They've told us this one is completely factorable, or it's going to factor, so we're going to have to end up with a remainder of 0, because this is what's left over when I divide that out. And notice that's going to be negative 6x squared plus 12x minus 60, so that when I change the signs, I do get a remainder of 0. So what I have is f of x is x squared minus 2x plus 10 plus 10. That was the factor that came from my complex zeros. And then my other one is x squared minus x minus 6. Okay? Now, we know that how this factored in my two zeros, my zeros of 1 plus 3i and 1 minus 3i come from this. Here, what I'm going to do is I'm going to factor that and see if it will factor like a normal trinomial. What will multiply to negative 6 and add to negative 1? That would be negative 3 and positive 2. So notice I have the zeros x minus 3 and x plus 2, which I can set both of those equal to 0. And I get the zeros of 3 and negative 2. So there answers the question. The question was, find all the zeros of that. So let's step back through that because that's a lot of stuff. All right, they asked us to find all the zeros. They gave us that 1 plus 3i is a 0 of f. Well, from there, I know since that's a complex 0, I know its conjugate is also a 0. So I know 2 of the zeros. So what I need to do is I need to divide the factors that led to this out of this polynomial to see what's left so that I can factor it and see what other zeros are there. So what I had to do was I had to get this factor, to get this 0, it came from the factor of x minus 1 plus 3i. To get this one, it came from the factor of x minus 1 minus 3i. And then what I did is I multiplied those together, which took a couple steps, a lot of stuff there. And it led me to x squared minus 2x plus 10 is the part that gave me these two zeros. Then I went over here and I divided that out of the original polynomial. And I got that x squared minus 2x plus 10 multiplied by x squared minus x minus 6 equals the whole thing. Then with that x squared minus x minus 6, I factored it so that I could find my other two zeros, set them each equal to 0, and I found that my other two zeros were negative 2 and positive 3. So that is a bit of a process. They make it look real easy because they just do a bunch of steps in the head, in the middle there. But there's the long division, and there is what we're doing. All right. So that's the factored form over reals. And that's really all we're going to be doing. That's it. And I don't think we'll have an assignment on the assignment. It shouldn't be quite that difficult. Biggest thing, remember, if you have a complex 0, its conjugate is also a 0. They come in pairs. Okay? So what they'll be doing is giving you one of the complex zeros. You have to know that the other one's there, and you want to multiply them together in their factored form so you know what to divide out. And then I will go ahead and activate I could stop sharing my screen. I need to stop the screencast. No, there we go. Pause.